What about the data that I'm accessing inside the region hash pragma OMP task? Which data am I referring to? That's a very important question. The thread which created it. So here is some data that I've defined, right? Let's say int I, and then I say hash pragma OMP parallel, and inside this now I say int j, okay? And again I write some code, and then I say hash pragma OMP task, and inside that I say int k. So I initialize I to be equal to 0, and I initialize j to be equal to OMP get thread num, and finally I print I comma j. So what is going to get printed over here? So let's worry about I later. Let's first talk about j. Okay. So j is what? J is OMP get thread num. So it's the thread number. So at this point of time, 4 threads are executing, right? 3 threads got launched, and one of them has thread ID 0, one of them has thread ID 1, thread ID 2, thread ID 3. Now let's say that thread 1 created a task which is now finally getting executed on thread number 2. Right? Is it clear? So I created a task on thread 1 and it finally got executed by thread number 2. What will get printed over here? 1 or 2 for j? I'm not asking for I right now. 1. Even though thread 2 is executing it, what you will see over here is 1. Why? Because when I'm executing this code and I'm creating this task, as a programmer, right, what are the variables that I'm referring to? What am I trying to refer to? I'm trying to refer to the variables that are just in the context over here. How can I refer to the variables for the thread where it's going to get scheduled? I don't even know which thread it's going to get scheduled on. So that is never my intention as a programmer to do that, right? As a programmer, my intention is always to access those variables which were just being accessed before this hash pragma OMP task. So what OpenMP does is that when it queues up a task, it also associates some data environment with it. By default, what it does is it creates a new copy of all these variables that are in the context of the thread. Alright, so at this point of time when this task is encountered, it creates a new task. It also creates a new variable j, a new variable start, and a new variable end. It allocates memory for these variables and copies the content from whatever the value was just before this task was initiated. Alright, that's why in this what you'll see is that the value of j, start and end will be just what you intended it to be, right? Start will be I, end will be I plus step size minus 1. That's what will be passed to the task.
Can we say that when thread number 1 created the task and the task is taken upon by thread number 2, so although thread number 2 has all those variables with some memory address, thread number 2 with the same, means like it created some other memories. For thread 1 it was j, but for thread 2 it is not actually j but some other memory address in his
Yeah, so additional memory is being created here, right? A copy is being created. It's not the same variable. It's not the same memory location. A fresh copy is being created. So that is the default behavior.
But this loading and unloading part will come in, will it not copying and then loading into registers and then that's the...
There is some overhead, but that's okay, right? That's like same overhead as you invoke a function.
There won't be some cache for that. Initially means for thread number 2 it has to load it from the...
So, okay, you're getting into something deep over here. You're saying that this code was executing on thread 0, which was executing on some core, right? And the data resided in its own cache or registers, and now you spawned off the task, which is getting executed on some other core, which has its own cache and registers, and therefore when it starts executing the code, it's not going to find those variables in the cache or the registers, and therefore it's going to have to load it. Yeah, that's true.
So if I have a heavy array,
But you never pass arrays. You pass pointers.
you pass chunk of arrays.
No, you don't even pass chunks of arrays. You pass the pointer to the starting of the array or a particular location of the array. But yeah, that is a fair point, that if you've already, let's say, taken an iteration over the data and it's in the cache, right? Let's say the entire array is in the cache, and now you're offloading the processing to another task. The copying of this variable is not the issue, because what you'll pass to the other thread is just a pointer to where you want it to start working on in the array. That pointer copy is just a 4 byte or 8 byte copy, right? That pointer is going to get loaded by the other core. That's not an issue. That's fine. That's one miss, right? One cache miss. But after that, now if it has to traverse the array, yes, it's going to load all the elements of that array to process it, right? That's something you have to be aware of if you're trying to shoot for that ultimate performance. Right? If you've already loaded that data in one core and then you're creating a task which is going to work on half that data, and it's going to have to reload it in the cache, yeah, you have to be careful about those things. These are minor things. I don't think you should be worrying about this data being copied in and out, right?
So in the example that we saw, ijk, if I were to do k equal to going to get thread num, you would get the actual thread num. The one which
Yeah, here if I said k equal to omp get thread num, I would get the thread which is executing this task. Alright, we saw this here. From inside also we printed which is the task computing the sum, right? And we saw that there was a different task which was actually computing the sum. Alright, so all the variables that are defined after hash pragma omp parallel, where the parallel region starts, all variables that are defined after that, if I access them inside the task, actually a new copy is created for them, right? This is same as scoping the variable as first private. First private j. So just like you have shared and private, right? Similarly, you can specify a variable to be first private. What that says is that create a copy of this variable and initialize it to the value just before this point. Okay, so you can actually use first private even in hash pragma, OMP, for and other places, right? Wherever you are starting a new region, you can specify first private, just like you specified shared and private. All right. So this is the default behavior in tasks. Variables which are declared after hash pragma OMP parallel, once the parallel region starts, all of them are treated by default as first private. Okay. All right. What about these variables which are outside the hash pragma OMP parallel?
they are global.
They are global. Even the threads were viewing them as global. So why should the tasks view them as private? Right? Why should the task have a private copy? I mean, the threads also wanted to view the same copy, global copies. As a programmer, I probably wanted to access the global variable, right? When I was trying to access that inside the task. So that's why these are treated as shared variables. Okay, so this is equivalent to saying here, shared I. Okay. So let's go back. We actually already did this, so without explicitly mentioning it. But if you see this code, right, sum plus equal to psum. So we accessed sum. Sum was actually a global variable declared outside the parallel region, right? So I was actually accessing the same copy of sum every time. And what about k? This is private. This is inside the task. Right, so I'll create memory for it which is just associated with the lifetime of the task, and once the task is over, that memory will be gone. Right, so this is simple. This has nothing to do with the outside world.
What do we mean by first private?
First private. So you remember private, right? So I have a variable int I and at some point of time I decided to create some threads, and I said I is equal to omp get thread num. I wanted to get the thread number, but I is declared outside, so I had to explicitly say private I, right? You remember this, right? That's what private does. At a separate memory location, it creates space for I. The only difference is first private does exactly the same thing, just that it initializes this I with whatever was the value just before this parallel region is encountered. That's all, nothing else. It just initializes that value. So if I said int I is equal to 10 over here, it will copy that 10 over here. If I print I here, I will get the value 10. Right? Of course, if I print it over here, I'll get the thread number, but if I print it over here, I'll get the value 10. If I said private I and I printed the value over here, I would get some garbage. Right? Clear? It's nothing but private with initialization, that's all it is.